Welcome to the RBFS Fundamentals Training Series. In this part of the series, we are introducing the RBFS command line interface. You'll learn how to access your network device, navigate through the system, configure key settings, and monitor vital components. Plus, we'll walk you through configuring network interfaces, routing instances, and static routes so you can get everything up and running. But before we jump in, a quick disclaimer. This training video is provided free of charge for non-commercial use. It's designed to help you quickly get up to speed with RBFS, but it doesn't cover every single configuration option. Things may change in future versions, so always keep an eye out for updates. Here's what we'll cover in this session. First, we'll break down the RBFS CLI, with a quick look at white box switches and the software layers that power them. We'll give you a set of essential operational commands to monitor system health and performance. Next, we'll dive into the configuration database, showing you how to tweak settings, roll back to previous versions, and save configurations to a file for future use. Once the box is up and running, we'll guide you through configuring the network interfaces. Moving on, we'll briefly touch on routing instances and static routes, including how to set them up. Finally, we'll wrap up with a look at user authentication configuration. In this section, we will provide a short overview on white box switching and the RBFS software layers. We won't get into bits and pieces, but we'll lay out the essentials so you can effectively interact with the box at various levels. We'll also walk you through the command line prompt, covering the basics of CLI navigation and how to leverage built-in help to speed up your workflow. Before we dive into the RBFS CLI, let's take a brief look at the hardware and software components involved. We won't go into the full details of the RBFS architecture here, but we want to provide enough background so you can better understand the context. RBFS stands for Rtbrick Full Stack, a network operating system that runs on white box switches. While RBFS can also run as a virtual instance on a server, this presentation will focus primarily on its deployment on white box switches. The fundamental concept behind white box switches is disaggregation, which refers to the decoupling of hardware and software components. Disaggregation provides greater flexibility and fosters innovation, breaking the vendor lock-in commonly seen with traditional networking devices. The terms white box switch and bare metal switch are often used interchangeably. However, technically, a white box switch has an operating system installed, while a bare metal switch does not. A white box switch is a network device that uses generic, off-the-shelf hardware components. This approach offers flexibility and cost savings compared to proprietary hardware. White box switches typically consist of several key components, each playing an essential role in the switch's functionality. Here are the primary components of a white box switch. The chassis houses all internal components of the switch. White box switches come in various form factors, such as one-unit rack-mounted units or larger chassis-based designs. The printed circuit board is the medium through which various components are interconnected. In personal computers, the PCB is often referred to as the motherboard. The CPU, along with memory, is responsible for executing the control plane functions of the switch. It runs the network operating system, which is often based on Open Network Linux. RBFS runs as a Linux container on top of ONL. The console port, out-of-band management Ethernet port, and USB port of the white box switch are all connected to the CPU. The switching ASIC stands for Application-Specific Integrated Circuit, is a specialized integrated circuit designed for packet forwarding and processing. It is responsible for high-speed packet switching and routing, enabling data to move efficiently within the network. Currently, RBFS supports Broadcom Qumran 2C, Qumran 2A, and Qumran AX-based white box switches. The physical network interfaces of a white box switch connect directly to the switching ASIC. This is crucial because, for in-band management access to the switch, the ASIC must forward management traffic to the CPU. The power supply provides electrical power to the switch, ensuring continuous operation. White box switches may include redundant PSUs for improved reliability. The fans maintain safe operating temperatures, as the switch components can generate significant heat. The baseboard management controller is an optional component in some white box switches. It is a specialized microcontroller responsible for out-of-band management tasks, allowing remote monitoring and control even when the main CPU is offline. It's important to note that the BMC and the CPU operate independently. The BMC has its own firmware and processing capabilities, enabling it to function even if the main CPU is non-operational. We do not cover the BMC in this presentation. The RBFS command line interface is the primary user interface for interacting with RBFS, enabling users to monitor, configure, debug, and maintain the system. The RBFS CLI is built using ClickSyn, a scalable FreeYong-based configuration tool that provides support for data store, netconf and restconf interfaces. The RBFS CLI offers operational commands to display system states, clear sessions and counters, reboot the system, and more. It also includes commands for modifying configurations, such as set and delete. The RBFS CLI operates within a Linux container named Rtbrick. This container houses multiple microservices, known as daemons, which are the core components of the RBFS ecosystem. These daemons communicate with each other through a centralized in-memory data store called the Brick data store. In this video, we'll focus on the daemons relevant for accessing and managing the device, such as the SSH daemon and Telnet daemon. Containerization provides a logical layer that enhances application security, flexibility, and portability by offering isolation. This RBFS container is hosted on Open Network Linux, an open-source Linux-based operating system designed for whitebox switches. The ONL controls the out-of-band management Ethernet interface and the serial console port. Additionally, several infrastructure services, such as the API Gateway daemon and Control daemon, run directly within the ONL layer. The API Gateway acts as the entry point, securing all REST API traffic by authenticating requests. Once authentication is successful, the Control daemon forwards requests to the relevant daemons, such as the restconf daemon or the operational state API daemon, which reside within the RBFS container. Device access via SSH or Telnet is supported through either the out-of-band management interface or physical network ports connected to the switching ASIC. In the case of out-of-band management, SSH and Telnet packets are routed either to the ONL layer or directly to the container layer depending on the port number using predefined IP tables rules. While the ONL host is only accessible through the out-of-band management interface or serial console port, services such as SSH running within the LXC container can also be accessed via in-band management through physical network ports. By default, in-band management is disabled. Once enabled, a Linux kernel interface is created in the LXC routing table, and routes from the in-band management table are downloaded to the Linux container. Access to the Rtbrick LXC container is provided using the standard SSH port 22 with a username and either password or an SSH key. This applies to both out-of-band access via the dedicated out-of-band management interface and in-band management, if configured. Once you've successfully logged into the container, you can start the RBFS CLI using the CLI command. If you wish to log into the ONL layer, you can use the same username but must connect via port 1022 instead of the standard SSH port. Access to the ONL layer is only possible through the out-of-band management interface. Alternatively, you can use the serial console port, which also provides direct access to the ONL layer. From the ONL layer, you can move to the Rtbrick LXC container using the rtbssh command. By default, the container name is Rtbrick. Additionally, the ONL layer provides access to the BMC via the ipmitool command, as well as to the ONIE bootloader via the ONIE shell. The Open Network Install environment is a combination of a bootloader and a small operating system designed for network switches, providing an environment for automated provisioning. ONIE enables the initial configuration of the out-of-band management interface via DHCP and facilitates the download and installation of a software image. We've identified different levels in RBFS, the ONL, the Rtbrick container, and the RBFS CLI itself. To ensure users always know their current level, the system displays distinct prompts for each. All prompts share a common format. They begin with the username, followed by an @sign. At the ONL level, the prompt includes the word ONL, followed by a greater than sign, the hostname, a colon, and finally, the current working directory in the ONL, ending with a $sign. The hostname is taken from the /etc/hostname.host-os file and is typically learned via DHCP. At the LXC level, the prompt closely resembles the one at the ONL level, except that instead of ONL, the @sign is followed by a static hostname defined in the /etc/hostname file. This hostname is usually the container name, typically Rtbrick. Once the RBFS CLI starts, the prompt changes. It resembles the one at the container level but displays the mode instead of the working directory. Additionally, the prompt ends with a greater than sign rather than a $sign. Before diving into the RBFS CLI, let's first cover how to access the ONL layer of the switch. To do so, initiate an SSH session on port 1022 instead of the default 22. Since this switch has not been configured yet, no user accounts have been created. The default user is supervisor, with the password also set to supervisor. Upon a successful login, you'll see various information, such as the device name, platform type, which indicates the ASIC in use, and the device model. In this demonstration, we are using RBFS version 25.1.1 along with a multi-service edge image. As mentioned in the previous slide, you can identify the ONL layer by the prompt, which will display the word ONL after the @sign. At the ONL level, there are two key commands we'll briefly explore. The ONI shell command grants access to ONIE. ONIE is a micro-Linux environment that serves as a bootloader and installer. The IPMI tool allows communication with the BMC, if present in the system. The BMC shares the out-of-band management interface with the CPU, and the IPMI tool can be used to control this interface. It's important to note that the IP address of the BMC is in the same subnet as the CPU, but distinct from it. To view the containers running on the ONL, use the lxcls command. As expected, only one container, named Rtbrick, is currently running. You can switch from the ONL layer to the container by using the rtbssh command, followed by the container name. Once logged into the container, you'll notice that the prompt changes to display the container name, rather than ONL. In addition to SSH, the ONL layer can also be accessed through the serial console. Let's briefly demonstrate this by logging out and establishing a connection via a terminal server. The prompt confirms that we are in the ONL layer. During the demonstration, we discussed ONIE, so here is a brief summary. The Open Network Install environment is a small, open-source, Linux-based operating system designed for bare metal switches. The ONIE project is maintained by the Open Compute project. Its primary function is to act as a bootloader and installer, enabling the switch to install and run a network operating system of choice. ONIE allows network operators to install various network operating systems onto the switch without relying on a pre-installed operating system. This flexibility enables the same hardware to run different software stacks, depending on the needs of the network. When a switch powered by ONIE starts up, it first boots into the ONIE environment. After obtaining an IP address, usually via DHCP, ONIE searches for a boot image source by looking for a server, such as a TFTP or HTTP server, that holds valid NAS images. Once the correct image is identified, ONIE downloads and installs it on the switch. The system then reboots, running the newly installed operating system. In the event of a failure or corrupted images, ONIE offers options for recovery or rescue. Additionally, ONIE supports the upgrading of hardware components, including FPGA firmware and BIOS images. The Intelligent Platform Management Interface is an open standard hardware management interface that allows you to communicate with the baseboard management controller of platform hardware. The BMC, a dedicated microcontroller, acts as an intermediary between system management software and the platform hardware. The BMC can be accessed either directly via the out-of-band management interface or the serial console port, which it typically shares with the CPU. Alternatively, it can be accessed in-band from the Open Network Linux using the IPMITool utility. The BMC monitors hardware resources, such as sensors, and can send alert messages over the LAN to indicate potential system failures. It also performs tasks like remote power on and power off and provides console access. Now that we've seen how to access ONL and the available functions at this level, let's turn to our main topic, the RBFS CLI. To begin, we'll log into the system via SSH, using the default port 22. Since we haven't created a custom user yet, we'll use the predefined supervisor user again. After logging in successfully, we'll get into the Rtbrick container. Here, we'll see a wealth of information, including the RBFS version, image type, ASIC used, and switch mode. The prompt will confirm that we're in the Rtbrick container. Next, we'll start the RBFS CLI by running the CLI command. Once executed, the prompt will change. For demonstration purposes, we'll enter the command show CLI. Since we're unsure of the available options, we can type a question mark to see the list of available options. While this won't appear in the terminal, it will display the options, which in this case are settings and tree. Let's start with the tree command. For convenience, we can simply type T and press the tab key to autocomplete the command. The output is lengthy, and by default, paging is enabled in the CLI. This means the output is displayed one page at a time. We can navigate through the output using the up and down arrow keys. To jump to the end of the output, press Shift-G. To return to the first page, simply press G. You can also search within the output by typing / followed by the search term. This will take you directly to the first matching result. To exit the output view, press Q. If we run the show CLI tree command again, we can press Ctrl-A to jump to the beginning of the line, and Ctrl-E to jump to the end. Pressing Ctrl-L clears the screen and displays only the current command. The history command will show a list of the most recent commands entered. As mentioned earlier, if you'd prefer to disable paging, you can do so by running paging off. You can also toggle syntax coloring in the terminal using the color on or color off commands. Syntax coloring is enabled by default. Two useful Linux pipelines are available for show commands. grep, to display only lines containing a specific expression, and count, to count the number of lines. At this point, it's worth noting that you don't necessarily need to enter the RBFS CLI interactively to execute a command. The CLI command allows you to run a single command directly from the container shell by using Option -1. After taking the first steps in the RBFS CLI, we want to briefly summarize our findings. The RBFS CLI is launched from the container shell using the CLI command, which changes the shell prompt to indicate the CLI environment. Alternatively, individual commands can be executed directly from the container shell using CLI-1, bypassing the interactive CLI session. For all show commands, the CLI supports output processing via Unix-style pipelines with grep and count. At present, no additional filters are supported. The CLI provides interactive assistance mechanisms for users unfamiliar with specific commands or their syntax. At any command level, entering a question mark displays a list of available commands or options. Additionally, command completion is supported via the tab key. By default, paging is enabled for lengthy output, displaying content one screen at a time. Navigation within paged output can be performed using the up and down arrow keys. Pressing G navigates to the beginning of the output, while Shift-G jumps to the end. Searches can be initiated within the output using / followed by a string. Backward searches can be performed using $? followed by a string. The display can be exited by pressing Q. Paging behavior can be toggled on or off. It is enabled by default. Similarly, syntax highlighting can be controlled using the color command, and is also enabled by default. Finally, the history command provides a list of the last commands executed. Let's explore some useful commands for monitoring a switch, starting with the show platform command. In RBFS, platform refers to the chipset used as the ASIC in the switch, such as Q2C, Q2A, or QAX. For testing purposes, RBFS can also run on a server, in which case the platform is virtual. The show platform command also provides additional details, such as the presence of a coprocessor, like the Broadcom OP2 used in this case, and displays the switch's manufacturer and model name. The show version command provides the RBFS version, here 25.1.1, and the role of the image. RBFS supports various roles that optimize images based on their functionality. These include the multi-service edge role, which offers the most features, as well as the spine, leaf, and L2BSA roles. In addition to platform details, the command also specifies the UUID under which the image can be downloaded from the RBFS image store. Since a software image consists of multiple packages and individual daemons can often be updated, the show version detail command also displays the version of each component. The full functionality of an RBFS installation is available only with a valid license. Without a license installed, you can evaluate RBFS for up to 7 days. Rtbrick also offers an evaluation license for 28 days upon request. You can check whether a license is installed using the show system license command. The control plane of a white box switch includes the CPU, memory, and storage. You can retrieve information about these components using the show CPU, show memory, and show disk commands. All three commands offer the summary option to get an overview, and the usage option to check current resource utilization. You can also view CPU and memory usage at the process level using the show process usage summary command. This show process usage command provides options to display details for a specific process, based on either the process name or process ID. The show sensor command provides information about the physical components of the switch, including fans, power supplies, and temperature. Monitoring system resources is crucial for analyzing device health. RBFS includes a dedicated daemon called ResMonD to discover and monitor the resources just mentioned. It is generally recommended to collect this telemetry data periodically using Prometheus and store it in a time series database. A device running RBFS has the link layer discovery protocol enabled by default. You can monitor discovered remote devices using the show LLDP neighbor command. If a software daemon crashes, it typically creates a core dump file containing the process's state, such as its address space at the time the process terminated. These files are located in /var/crash/rtbrick. You can check for the presence of core dump files using the show core dump command. If a core dump exists, provide it to the Rtbrick support team for further analysis. If a switch needs to be restarted, you can use the reboot command. The reboot command offers the option to reboot the container only or the whole device. To conclude this section, I've summarized the commands on the following 3 slides for your reference. We've already covered the show platform and show version commands, which provide information about the hardware and software in use. Additionally, you can check the switch's capacity using the show hardware limits and show hardware resources commands. The show system license command displays the installed software licenses. We've also reviewed the commands for displaying CPU load, memory usage, and disk usage. For the show CPU, show memory, and show disk commands, the summary and usage options provide detailed information, respectively. The show process usage command breaks down resource usage on a per-process basis. You can query the physical parameters of the switch using the show sensor command. This command provides options for monitoring LEDs, power supplies, fans, and temperature. By default, LLDP is enabled on all interfaces. You can verify this with the Show LLDP interface command and display all neighbors with Show LLDP neighbor. Core dumps generated during daemon crashes can be viewed with the Show Core Dumps command. If a core dump is available, the stack trace option provides valuable information for Rtbrick support. If needed, you can restart either the Linux container or the entire device, including the ONL, using the reboot command. In order for a switch to participate in IP routing or provide services such as subscriber session handling or network address translation, it must first be configured. In the next section, we will take a closer look at how to perform configuration using the RBFS CLI, how to view the configuration, in whole or in part, in various formats, and how to delete existing configurations. Upon starting the CLI, the system enters operation mode, as indicated by the prompt. In this mode, you can display system status and reset certain states, for example interface counters. The RBFS CLI offers two additional modes, configuration mode and debug mode. Debug mode provides additional commands useful for diagnosing and troubleshooting issues. These commands are intended for advanced users and are typically used under the guidance of Rtbrick support engineers. To enter configuration mode, use the switch mode config command. The RBFS CLI follows a structured configuration approach. Configuration commands are initiated with set, and removed using the corresponding delete command. RBFS configuration is managed by the configuration daemon, which uses CLI as the configuration backend. CLI is a configuration manager built on Yang models. There are two main ways to interact with CLI, via the CLI, by starting the interactive RBFS CLI and switching to configuration mode, or via the RESTconf interface. In this video, we will focus exclusively on the CLI-based method. Once a configuration change is submitted to configuration daemon through CLI, conf is responsible for distributing the configuration to the appropriate internal services. It does this by creating configuration tables and exposing them via a publish-subscribe mechanism. To prevent configuration inconsistencies, state-of-the-art network operating systems such as RBFS support a dual configuration model, the running configuration and the candidate configuration. The running configuration represents the currently active configuration. The candidate configuration holds changes that are being edited but not yet activated. This separation helps prevent accidental activation of invalid configurations, for example, due to typos. To apply changes, users must explicitly commit them using the commit command. After committing, the running and candidate configurations are synchronized until further changes are made. Note that configuration changes made via RESTconf are applied directly to the running configuration. Let's return to the terminal window and enter configuration mode. The switch mode command provides three options: operation, which is the mode currently in use, debug, and config. We choose config, and will notice the prompt changes to indicate the new mode. To view the active running configuration, use the show config command. By default, the output is displayed in JSON format. The show config command supports several options. On the one hand, you can change the output format. Valid options include JSON, netconf, set, and text. On the other hand, you can restrict the output to specific parts of the configuration for better readability. Running show config JSON will produce the same output as show config, since JSON is the default format. Next, let's view the configuration in set format. This format is particularly useful because it's the one we'll use to modify the configuration shortly. You'll see that the current configuration is minimal, showing only the system hostname and some interface speed settings. Alternatively, you can display the configuration in netconf format. As mentioned earlier, you can also filter the output by configuration hierarchy. For example, to display the configuration for a specific interface in set format, use show config set interface IFP 0/1/25. If the output is empty, it means that no configuration has been applied to this interface yet. Let's try querying another interface for comparison. If we want to modify the configuration, we use the set command. The set system command offers some interesting options such as setting the hostname set system host element name command. It also allows to set the NTP server or create local user accounts. The set system license command can be used to install a software license enabling the software once the trial period is expired. For demonstration purposes, we enable the system to load the last configuration after reboot by running set system load last config true. By default, configurations are not persistent across reboots. Setting this option ensures the configuration is retained. After executing the command, we check the configuration using show config set system. You'll notice the line you just added is not present. This is because show config displays the running configuration, while changes first go into the candidate configuration and are not automatically enabled. To view the differences between the candidate and running configurations, use show diff. Again, we can add the set option to view the difference in set format instead of JSON. Activation of configuration is done via the commit command. Once committed, we use show config again to confirm that the load last config setting has been applied. The show diff command will now show no differences between the running and candidate configurations. The show commit log command displays the history of configuration changes, including an rollback ID, a timestamp, and the username of the individuals who executed the commit. Rollback ID 0 always refers to the current running configuration. If we wish to revert to the previous configuration, we can use the rollback 1 command. Executing show diff once again to confirm that the candidate configuration has been updated with the previous configuration. It's important to remember that the rollback command does not automatically activate a previous configuration, you must still run commit to apply it. If we have made changes to the system that you no longer wish to apply, then you can execute the command discard, which deletes all uncommitted changes in the candidate configuration. The discard all command removes all configuration. While the show commit log provides useful metadata like version numbers and timestamps, it may be helpful to describe the changes. RBFS allows you to include a message with a commit. If your message includes spaces, wrap it in quotation marks. It is also possible to store the configuration into a file using the save config command. On the contrary, you can use an existing configuration file and load it to the system using the load config command. By default, this replaces the existing candidate configuration. If you prefer to merge the file contents into the current candidate configuration, use the merge option. To wrap things up, let's quickly go over the key commands we've covered, just as a refresher. First, the show config command displays the current running configuration. By default, it shows the output in JSON format, but you can change the format if needed. You can also narrow it down to a specific section of the configuration. And yes, these options can be combined. When it comes to making changes, all configuration starts with the set command. If you need to remove something you've previously configured, you'd use the delete command. Now, something important to note, unlike some other vendors, RBFS doesn't let you jump into a part of the configuration and work from there. In RBFS, you always need to enter the full path of the command. However, this also lets you delete entire branches in one go. For example, delete system NTP will remove all configured NTP servers. To compare changes, the show diff command shows what's different between the candidate configuration and the one that's currently active. If you've made changes but want to undo them, just use discard. Once you're happy with your changes, you activate them using the commit command. You can even add a message to your commit, which is helpful when you want to document major changes. If you need to save your config to a file, or load one back in, you'll use save config and load config. RBFS automatically keeps the last 50 configurations. You can view them with show commit log. These are listed in reverse order, ID 0 is the current running configuration, ID 1 is the previous one, and so on. You'll also see any commit messages, which makes it easier to track what changed and when. The rollback command lets you pull up any of these earlier configs and load it into the candidate configuration. Just remember it won't take effect until you commit it. Now here's a critical point: by default, RBFS does not keep the configuration after a reboot. This is intentional, especially in automated data center environments, where a configuration server holds the source of truth. But if you do want to keep the config across reboots, you can enable persistence with set system load last config true. Just keep in mind, if you're using zero-touch provisioning, this setting will still be overridden. Now that we've familiarized ourselves with the RBFS CLI and its various modes, we'll walk through some simple configuration examples in the following sections. We'll begin with configuring network interfaces, a task we frequently encounter in practice. RBFS supports a variety of interfaces, including both physical and logical types. A physical interface typically represents the physical ports on a hardware switch. For example, if P0/0/1 refers to switch port 1. At the physical interface level, you can configure parameters associated with layer 1 of the OSI reference model, such as link speed. For each physical interface, you can create one or more logical interfaces, also referred to as interface units in RBFS. A logical interface is associated with layer 2 operations. You can also configure layer 3 parameters, such as IP addresses, on interface units and assign them to routing instances. A loopback interface is used to represent and identify the device itself. Loopback interfaces are preferred because they are independent of the status of physical ports, meaning they will always be up. Linux Virtual Ethernet interfaces connect an LXC container to the Linux host OS. In RBFS, a Virtual Ethernet interface to the Linux bridge is created by default. In virtual topologies, you can create additional Virtual Ethernet interfaces and Linux bridges. RBFS host interfaces correspond to Virtual Ethernet interfaces in RBFS. Memory interfaces are virtual interfaces used for creating virtual topologies, enabling communication between multiple RBFS containers. RBFS interface numbers correspond to the port numbers on the switch faceplate. An interface name follows this format: IFP-chassis ID/front panel block number/port. For example, if P0/0/0. The chassis ID is always 0 for the currently supported platforms. The front panel block represents a group of ports on the faceplate, and the port number corresponds to the physical port on the switch. Virtual interfaces follow the same naming structure. For example, LO0/0/0. One or more logical interfaces can be created for a physical interface. The numbering is similar to that of the physical interface. However, the name changes from IFP to IFL, and the unit ID is added, making the logical interface unique, for example IFL 0/0/0/10. You can also create logical interfaces for virtual interfaces, such as loopback interfaces or host interfaces. In this case, the name of the logical interface remains unchanged, with only the unit ID added. For example, LO0/0/0/100. As of RBFS version 25.1.1, Rtbrick supports hardware platforms from Edge Core and UEFI Space. Both vendors offer switches based on Broadcom's Qumran Q2C, Q2A, and QAX chipsets. The supported interfaces on these switches range from 1 gigabit per second to 400 gigabits per second. The following table lists all currently supported switch models, including the installed ports, and provides their corresponding RBFS names. For more details about the switches, please refer to the platform section of the RBFS technical documentation or consult the vendor's datasheets. In this presentation, we will be using an UEFI Space S9600-72XC switch. Let's return to the terminal window and configure port 20 on this switch using the set interface IFP 0/1/20 command. The question mark provides a list of available options. At the interface level, these configuration options pertain to Layer 1 properties. For example, you can shut down the interface using the admin status down option, enable auto-negotiation, or set the port speed in the case of multi-rate interfaces. For documentation purposes and ease of operation, it is recommended to set an interface description. Let's configure the description and indicate the remote port in the description text. Next, we will move on to the logical interface configuration using the set interface IFP 0/1/20 unit command. You can choose any unit number, but for unstructured interfaces, it is common practice to use unit 0. At the logical interface level, you can configure various Layer 2 and Layer 3 options. In this case, we will only set the IP address using the address subcommand, followed by the address family, in our case IPv4, and the IP address 172.16.10.1/24. Configuring IPv6 addresses is done the same way. To verify that the configuration works, we commit the configuration and execute a ping to the directly connected node 172.16.10.2. The ping command sends ICMP echo requests to the specified IP address and counts the ICMP echo replies received. As we can see, there are no packet losses. We will configure an interface that uses VLAN encapsulation. Again, we use the command set interface, this time IFP 0/1/26. We define unit 100 and set the VLAN to 100. Additionally, we assign an IPv4 address to this logical interface unit, just as we did for the plain Ethernet interface earlier. On the same interface, we can configure another unit to support double-tagged VLAN encapsulation. The outer VLAN is configured using the VLAN command, while the inner VLAN is defined with the inner VLAN command. The IPv4 address configuration remains identical. We activate the configuration and run the ping command again to verify that both interfaces work as expected. For IP routing, it is very useful to have an interface that is independent of the status of any individual physical port and remains stable. These interfaces are called loopback interfaces. We can configure a loopback interface and assign an IP address to it using the command set interface LO 0/0/0 unit 0 address IPv4 192.168.0.1/32. To get a list of all IP addresses configured on the system's interfaces, RBFS provides the show interface address command. If the capacity of a single interface does not meet the bandwidth requirements, and using multiple interfaces in equal cost multipath mode is not desired, multiple interfaces of the same speed can be bundled into a link aggregation interface. For example, you can bundle 4 10 gigabit per second interfaces into a single 40 gigabit per second interface. In RBFS, link aggregation is configured using the set link aggregation interface command. The supported interface names are lag 1 to lag 99. The minimum configuration requires setting the mode to either LACP or static and defining one or more member interfaces. Once the link aggregation interface is created, all Layer 2 and Layer 3 configurations are applied using the set interface command, just as with any other physical interface. After activating the configuration, we can use the show interface address command again. It takes a couple of seconds for the newly created interface to appear in the list since we've chosen LACP mode, and the link aggregation control protocol needs to establish communication with the remote side. We can also verify that IP connectivity is up by using the ping command. The set link aggregation interface command offers additional options. For example, the minimum link count defines how many member interfaces need to be up for the link aggregation group to be considered active. Currently, we have two 1 gigabit per second member interfaces and need to transport up to 2 gigabit per second, so let's set the minimum link count to 2. The show lag command provides a list of all member interfaces, including their status, while the show lag detail command provides more detailed information. For demonstration purposes, let's shut down one of the member interfaces. Once it is down, we will observe that the link aggregation group interface also goes down because the minimum link count requirement is no longer met. We've already seen the show interface command, which offers several useful options. For example, the show interface summary provides a brief overview. The show interface address, which we have already used before, lists all configured IP addresses. The show interface logical command lists all logical units configured on the system. Last but not least, the show interface physical command provides a list of all switch interfaces, whether they are configured or not, and their physical status. The show optics inventory command lists all transceivers installed in the system, including type, vendor, part number, and serial number. If you are interested in more details, you can use the show optics interface command. The output of this command depends on the type of transceiver. A very useful command for troubleshooting is the show interface history command, which provides information about the transitions between different interface states. Let's summarize the results of our configuration for clarity. The physical interface is configured directly using the set interface name command. This command allows you to configure various layer 1 parameters, such as auto-negotiation, speed, and mapping when a breakout cable is used. It is always advisable to add a description. This simplifies management. Additionally, the interface can be administratively shut down with the admin status up or down commands. At the logical interface level, configuration is done using set interface name unit number. In addition to VLAN settings, defining the IPv4 or IPv6 address is particularly important at this stage. Now, let's take a brief detour into MAC addresses. Each Ethernet interface on a switch has a unique layer 2 MAC address. RBFS uses the manufacturer's MAC address range, if available and valid. You can view the platform MAC address with the show platform command. The MAC addresses for physical ports are assigned from this range in ascending order. If the system doesn't have its own MAC address range, RBFS defaults to using the Rtbrick MAC address range. To avoid MAC address conflicts, a hash of the chassis serial number is added. For virtual RBFS instances, the MAC address of the container management interface is used. Link aggregation is a technique used to combine multiple network connections into a single logical link. The primary goal of link aggregation is to increase bandwidth and provide redundancy. If one link in the aggregation fails, the traffic can continue to flow through the other active links without disruption. To create a link aggregation interface in RBFS, use the set link aggregation interface command. Here, you must specify the mode and add the member interfaces. Both static and LACP modes are available, with LACP being the recommended option, because it is a standardized protocol that automatically negotiates parameters between devices. Optionally, you can define how many member links must be active for the link aggregation interface to be active. The logical lag interface is then configured similarly to the interfaces discussed earlier, using the set interface lag name unit number command, with the appropriate layer 2 and layer 3 parameters. RBFS offers several interface commands for monitoring and troubleshooting. All of these commands begin with show interface. Depending on what you're interested in, you can use the physical, logical, and address options to get the relevant details. If you're focused on a specific interface, use the show interface name command, optionally with the detail or statistics options. The statistics option displays packet counters, which you can reset using the clear interface statistics interface name command. To view the transceivers installed in the system, use the show optics inventory command. Detailed information, such as the power level, can be obtained with the show optics interface command. For specific details on a link aggregation interface, use the show lag command. In this section, we introduce the concept of routing instances. We've already implicitly used routing instances when configuring interfaces. A routing instance represents a set of logical network interfaces and routing protocols. Each routing instance can support multiple address families, such as IPv4 and IPv6 unicast. Every routing instance has its own routing table for each address family, which is strictly isolated from the routing tables of other instances. This means that interfaces or routes learned in one routing instance cannot be accessed by another routing instance by default. You can think of a routing instance as a standalone virtual router. A logical interface is always assigned to a single routing instance. However, if a physical interface has multiple logical units, for example, multiple VLANs, these units can belong to different routing instances. If no routing instance is explicitly configured, the default instance is used. If we examine the show interface address command, we see that all interfaces are assigned to the default instance by default. The show instance command reveals that only this one instance exists on the system. Using the show instance default detail command, we can also see which address families are active. We now want to create a second routing instance, which can be done with the set instance name command. We'll name this new instance ABC, and enable both IPv4 and IPv6 unicast address families. After applying the configuration, we can confirm that a second instance has been created. However, unlike the default instance, this new instance doesn't have a router ID. The router ID is used by many dynamic routing protocols for identification and must be unique within the network. Typically, it is taken from a loopback interface assigned to this instance, but it can also be set manually. Next, we'll add interfaces to the new instance. For example, we configure port 61 with the command set interface IFP 0/1/61 unit 0 instance ABC. We also assign an IP address, as we've done previously. In RBFS, IP addresses need only be unique within a given instance, meaning the same IP address can be used in different instances. We repeat this process for a loopback interface. Using the show interface address command, we can verify that there are now two logical interfaces in instance ABC. To test their functionality, we can use the ping command. However, the ping command uses the default instance unless otherwise specified, so we must explicitly add instance ABC in the command to test the new interfaces. Let's briefly summarize the commands. Routing instances in RBFS can be easily created using the set instance name command. The address families used must be explicitly configured. Each routing instance has a unique instance ID, which can be set manually. General information about a routing instance can be viewed using the show instance name command. The routes belonging to a routing instance can be displayed using show route instance name. When using the ping command to test IP connectivity, be aware that it uses the default routing table unless otherwise specified. To test connectivity from a specific routing instance, you must explicitly specify the instance. In this section, we will introduce how to configure static routing in RBFS. Static routing allows a network administrator to manually configure routes. While this may seem like an administrative overhead, especially considering the availability of dynamic routing protocols, there are situations where dynamic routing is not desirable. For example, security concerns or systems that do not support dynamic routing might necessitate static routes. The main drawback of static routing is that it does not provide a mechanism to update routes if the network topology changes. If the network has no redundancies, this may not be a significant issue. However, it is clear that static routing does not scale well in large environments, and it is also more prone to errors. RBFS supports configuring static routes on a per-routing instance basis and allows for the addition of static routes across all address families. In the terminal, we can execute the show route command to display all routes present in the routing table. You will notice two types of routes, direct routes and RPND routes. Direct routes correspond to the interfaces we've configured so far, while RPND routes are host routes representing neighbors connected to those interfaces, discovered via ARP for IPv4 or IPv6 neighbor discovery. Let's add a static route to the default instance using the setInstanceDefaultStatic command. A static route consists of two components, a destination and a next hop. You can group multiple next hop parameters within a next hop profile and associate that profile with several routes. We begin by creating a next hop profile named UFI16, with the next hop set to 172.16.12.2. Then, we create a static route using the setInstanceDefaultStatic route IPv4 192.168.0.2/32 unicast UFI16, UFI16 being the next hop profile defined in the last step. This command works the same way for IPv6. After committing the configuration, the show route source static command will confirm that the static route has been added. You can verify that the route works by pinging the destination. Next, we create a second next hop profile named discard. In addition to the next hop IP address, we can add other options to the next hop profile, such as lookup instance. This allows us to install a static route that uses a next hop from another routing instance, enabling inter-instance routing. Another option is defining an exit interface, which is particularly useful when using the null-zero interface. This is a virtual interface used to discard network traffic. You can use this to create a static route that drops traffic, which is useful for blackholing unwanted traffic or managing address pool distributions. We now create a new static IPv4 route with this discard next hop profile. Using the show route source static command, we can see that the route is installed without a valid next hop, causing traffic destined for this route to be dropped. In summary, the setInstanceName static nexthop profile command is used to define a nexthop profile. This profile can contain a next hop address, an exit interface, or both. Multiple static routes can share the same nexthop profile. Static routes are created using the setInstanceName static route command, where you specify the address family, destination, and the nexthop profile. Additionally, you can assign a route preference to the static route. The route preference is used by the routing daemon to decide which route to add to the routing table when the same route is available from multiple sources. You can also add a community or extended community attribute to the route. These attributes are useful for tagging routes for later processing. We'll cover this in more detail in the BGP module. A conditional profile can be applied to the static route, allowing you to define conditions, such as a minimum route count, that must be met for the route to become active. We began this presentation by showing how to log into an RBFS system using SSH. This final section brings us full circle, where we'll now show you how to configure user authentication. So far, we've only used the predefined supervisor role to log into a switch with RBFS. However, in practice, multiple users often need to work on a system simultaneously, and it's crucial to ensure that each user can log in independently. Furthermore, different users typically require different levels of permissions. User authentication ensures that only authorized individuals have access to the system. With RBFS, user management can be handled either locally or centrally. In the local approach, usernames, passwords, and permissions are configured directly on the switch. While this method allows the system to function independently when central user management is unavailable, it has the disadvantage of requiring users to be created and deleted individually on each switch. Typically, only a small number of local users are defined to serve as a fallback when central management is down. With the central approach, users are typically defined on an authentication server. TACAX acts as a protocol between the switch and the authentication server, allowing the server to compare user credentials and permissions during an SSH login attempt. In both cases, you can customize the roles that define individual access rights. The only predefined user account available on an RBFS system is the supervisor account. Let's now create a new user called Bob. This can be done with the command set system user Bob. The command requires you to set a role for the new user. There are 3 predefined roles available: supervisor, operator, and reader. You also need to define a login shell for the user and, finally, set a password. While it's also possible to set an SSH public key, for demonstration purposes, we'll set the password to Rtbrick. By the way, you can change the default password of supervisor the same way. After committing the configuration, open a new terminal window and establish a new SSH session. Log in with the username Bob and the password Rtbrick. As you can see, access to the system is granted. At this point, we've configured user Bob with supervisor privileges. You can define additional roles using the command set system authorization global role. While we won't go into detail here, this command allows you to specify which commands a user can execute, using both whitelist and blacklist options, and control which tables and objects the user can access through role-based access control. As mentioned earlier, in large networks, it's recommended to use a centralized authentication server. RBFS supports TACACS authentication. By default, TACACS communication only works if the server is directly connected to the out-of-band management interface. In our case, the TACACS server is connected to interface IFP 0/1/61, so we need to enable in-band management using the command set in-band management instance. Previously, we configured unit 0 of this interface to belong to instance ABC, so we'll use that here. Then, set TACACS to true. Next, we need to enable secure management using the command set system secure management status true. We then define the TACACS server using the command set system authentication TACACS 172.16.101.2 in-band secret plaintext TACACS 123. The parameters are the IP address of the TACACS server and its key. Once the configuration is activated, verify that Bob is the only user locally defined. Finally, switch to another terminal window and verify that you can establish an SSH session using user Alice. We've seen a practical example of how to create a local user in an RBFS system using the set system user username command. To do this, you need to define the role, enter a password or SSH key, and specify a login shell. The predefined roles are supervisor, operator, and reader. However, it's also possible to define custom roles using the set system authentication global role command and specify individual permissions. For example, you can permit or deny the execution of commands. The Terminal Access Control System is a protocol that allows us to outsource user management to a central server. To set this up, you need to create a server with the set system authentication TACACS command and specify whether you want to use it in-band or out-of-band. You will also need to define a key. If TACACS is used in-band, you must define an in-band management instance and add TACACS. Note that when defining an in-band management instance, all routes for this instance are downloaded to the host routing table of the Rtbrick Linux container. As such, it's generally not recommended to use in-band management in the same instance as internet routing. Similar to TACACS, SSH access to the system can also be configured in-band. In this case, SSH must be added to an in-band management instance as well. SSH access can be authenticated using either a password or an SSH key. If you prefer to use only SSH keys for security reasons, you can disable password authentication with the set system authentication SSH password authentication false command. This brings me to the end of this presentation. I hope this session has been helpful, and I'd love for you to check out our other videos in this training series. Thanks for watching, and see you next time.